Okay. Keep refreshing just to make my stream, or make sure the stream is going up. It looks like it is. Refreshing. Okay, and we're getting sound. All right, so I think we're ready to go. Good evening, everybody, and welcome to Virtual Starry Nights, streaming live from the SFU Trottier Observatory. My name is Matthew, and I'm joined today by my colleague and friend and virtuoso of space, Sarah.
Hello, everybody. Hope you all are doing well. Matt and I are very excited to come to you from the observatory, virtually, of course. We've got a full itinerary ahead, and as you probably are aware, you may put your questions in the chat as we go along. And we have a few of our friends who are helping us out in the chat box tonight, including Kyle, Zena, and Karenbeer.
All right. How is everyone doing on sound? A little bit of an echo. It's a tiny echo. That could be on my end. We're doing our audio setup a little bit different, so there might be some echo from Sarah. I'll make sure I sit a little bit back farther from my mic when that happens. I was trying to. How did you get here? So this is Sarah's first stream, so we're all very excited for Sarah to be here. Sarah is a long-time member of the Trottier Observatory, but this is Sarah's first stream. So Sarah, how did you get into space, and why are you here working with us tonight, talking about space?
Oh, great. Yeah, I mean, space has been a big part of my life for a long time, as it has been for many people, and of course you as well. But I got into space through my undergrad at SFU, and I was actually around just when the observatory opened up in 2015, and I've been there ever since. I was one of the first students to get a set of keys in, and I haven't left since then, so you can't get rid of me that easily. But since then, I've worked at a few observatories around the world, including the Niels Bohr Institute at the University of Copenhagen and the University of Cambridge Observatories at the Institute of Astronomy. Just having some fun going around as I do my degrees and then nighttime in astronomy. But my daytime job is actually in public health research. So public health researcher by day and astronomer by night. Moonlighting, as you would say.
Yeah, we were talking about how you know when you've made it pro as an astronomer is that you're not an astronomer. You're also an astronomer at daytime, but as well as nighttime. Like that's how you know for sure. People are saying that they can't hear Sarah. Is Sarah clear for everybody else?
I'll give you a little test if you can hear me, or maybe not.
No? Is that just Warner, or is everyone okay for Sarah and sound? Kyle, can you hear Sarah okay? We don't know.
I think also Rhiannon mentioned in the chat.
Oh, okay.
That,
So everyone else seems to be able to hear you okay. Okay, good.
Great.
Great! Okay, that's perfect. I was testing today. I was trying to figure out what tone I wanted to open up the show with, and I was like, do I want to go with, hello everyone, welcome to the observatory, or more like, hello everyone, it's after hours at the Trottier Observatory. You're joining us because it's so much later than usual. So thank you everyone for joining us because it's so late, or much later than usual. So thank you everyone for tuning in. Okay, we're going to start with one of the brighter objects in the sky today because otherwise we'd be fighting with it entirely, and that is the moon. So we're going to do a big reveal here for the moon. Here we go. We're actually already pointed at it, so I'm going to increase our exposure timing. And here we are, looking at the moon. And I think we've actually drifted a little bit off target from where I want to go. Now, if you are looking at the moon right now, trying to figure out where we are pointed at the moon, you might notice that it's not quite recognizable because the moon is rotated in the field of view from our camera. So to show you kind of where we are pointed here at the moon right now, and I'm going to move us more in this direction because I want to talk about this area toward like the southern or southern area of the moon that we're looking at. And so I'm going to bring up our app, which is the PlaneWave app. This is the software that controls our telescope. It was designed by PlaneWave's instruments, and it is what we use to control our telescope. So right now, if you can see what are you looking at right now? Oh yeah, you can't see that. So the moon here is centered as it's selected as a target. Where the telescope is actually looking is this yellow spot over here, and I'm going to move it down because I want to look at this target down near the bottom of the moon. So here we go. Slowly moving the telescope over a little bit at a time. All right, there we go. And if I bring it back up, we should be looking at, so this crater here, that's sort of in the center of the screen, that has kind of a drop toward the center of it, is called Tycho's crater. And it's one of those really obvious craters that's on the moon's surface. And when you look at the moon, if I bring it back up here, kind of the digital image of it that's in our software called SkyX, it is also the part of the moon, when you look at it, that has kind of these big rays, these lines coming off of it from the center. And that's actually material that has been kicked up by the impact of whatever made this crater on the surface of the moon. The crater itself is dated to about 180 million years ago, which actually for a crater is quite young. That's not a very, very old crater at all. The crater itself is about 85 kilometers across. So this also gives you a sense of scale of what you're looking at on the moon's surface. So often one of the questions that we get when we're looking at the telescope through to the surface on the moon is, can we see the Apollo landing sites? And the answer to that is no, because if you think about the scale that we're looking at, that crater that you're seeing there, that's 85 kilometers across. You can imagine how tiny a landing vehicle is going to be within that crater. Actually, not even the Hubble Space Telescope is capable of imaging with enough resolution to see the Apollo landing sites. That can only be done with the Lunar Reconnaissance Orbiter. And I'm going to bring up one of the pictures from the orbiter. This is the Apollo 15 landing site, as seen by the Lunar Reconnaissance Orbiter. And you can actually see here, these are footprints and driving marks, tire tracks that are left over from the moon buggy. The moon buggy was first equipped on Apollo 15, so that was the first one it went up with. And so from orbit, you can see those details. And of course, because the moon has no atmosphere, meaning that there's no wind, and that means there's also no rain, then tire tracks and features like the footprints on the surface of the moon can last for millions and millions of years. Maybe there'll be a museum piece. Sarah, maybe you can pay like $20 in the future when space travel's a lot easier, go to the moon and see like Neil Armstrong's footprint in like a box of glass that's still like preserved over time. I don't know, what do you think?
That would be the dream, the absolute dream.
Wouldn't that be the dream? I think that'd be pretty cool.
Imagine going to the moon and as if you were catching the bus to go to work.
Yeah, exactly. Yeah, you know, you're just like, hey, let's go our day trip to the moon or whatever and come back, or maybe a week vacation because it takes a little while to get there. To give you also a kind of sense of dimension on the crater, it's about 4.8 kilometers deep, so that is a deep crater, and the rays that are coming off of it can be up to 1,500 kilometers long. So imagine if you have debris that's being kicked up by a crater, then there's nothing to slow it down except eventually gravity pulling it back down to the surface, but it's not going to be slowed by wind or anything like that. So if it's kicked up high enough, it's just going to keep going and going and going and going. Now, cool thing about Tycho's crater, it's named after Tycho Brahe, who was a Dutch astronomer. And interesting thing about Tycho Brahe, because he was kind of a neat guy, he was very passionate about his astronomy. And at one point in 1566, he got over a row with some other fellow astronomers about the helio versus geocentric model of the solar system. And in that fight, he pulled a sword. There was a sword fight, and his nose was cut off. So Tycho Brahe was a serious astronomer. He took his models and his publications very, very seriously. So 1566, poor Tycho Brahe gets his, he ends up in a fight. I don't think there's any astronomers that fight with swords anymore. And maybe that's a sad thing. Maybe that's some loss. I'm not sure.
Well, it's interesting that you mentioned Tycho, because I did actually get an opportunity to visit the ruins of his observatory. It's located on a tiny island between Denmark and Sweden called Wien. And that island it's very small. It's got a whiskey distillery and it's got the observatory, so it can tell you the priorities of that island. But the observatory is not standing anymore. There's just some old building crumblings, and they have a cool light show that goes on down in the depths. But yeah, it's an incredible observatory and an incredible museum that they've built alongside it. So if you ever get the opportunity to go to Denmark or Sweden, you can take a little ferry and go to this island called Hveen, H-V-E-N, and visit this really cool observatory.
Sweet. That's awesome. Okay, one other place we're going to visit on the moon is one of the landing sites for Apollo, since we were talking about Apollo. So what I'm going to do to navigate back there again, or to help me to do that, is to go back to SkyX, because everything is a little bit oriented sideways. And we want to go here. That's where we're going to be going. And some of you who are savvy out there might already know which landing spot this is. And let's go. Closer and closer. Almost there. One more over. There. That is almost perfect. Okay, so let's go back to our moon. And go back to Sharp Cap. Here we go. Okay, we are looking. This patch down here is a basaltic lava flow that is since solidified. So they're actually known as mare, or seas. This one is the Sea of Tranquility, and it's around this region here, if I've got my orientation right, more here, around here, more or less, that Apollo 11 landed. So that is our first landing spot on the surface of the moon. Now, why do these regions look like this? So these areas on the moon are basaltic. So they're basically lava flows that have melted and cooled. So this would have been like an ocean of lava, basically, on the surface of the moon. They were called seas in the past because when we were observing them from Earth before we went there, we thought maybe they actually were water. We didn't know. And most of the things that were named on the moon were named by an Italian astronomer, and his name was Giovanni Battista Riccioli. And so the things that he has named on the moon are since the names that have stuck. And so we kept them. And so he called them mares, again, Latin for lake or sea, and they have kept around. These oceans were formed about 3.6 to 4.2 billion years ago. One of the things about them, we don't actually know why our side of the moon has most of them. So only 16% of the moon's surface is covered with these seas. But if you look at the moon, it looks a lot more than coverage than that. But you have to remember, our side of the moon looks different than the other side. So if I bring up a folder here, actually have a picture of the far side of the moon that'll open up for you. And you can see it doesn't have nearly as many of those dark basaltic lakes or oceans of lava on it. And there's kind of an ongoing debate as to why that is. We wonder if it has something to do with the side that faces us. So the moon has something called tidal lock to our side of the Earth. And so it rotates at the same speed on its axis as it circles the Earth. And so we're always looking at the same side of the moon. That's because of the Earth's gravity has locked the Earth's rotation, or the moon's rotation, to us. And so it might have something to do with that, but we're not exactly sure. But yeah, basically oceans of lava that have solidified on the moon's surface. And one more quick thing, and then I'm going to pass it over to Sarah. I was going to leave the moon, but I realized there's actually one more neat thing that we can look at on here. And it is over in this direction. Okay, one more second here.
The far side of the moon definitely looks more like a golf ball.
Yes, it does. Yeah, often I'll pull it up sometimes in presentations, and I'll be like, "What is this?" And everyone says, "Is it like Mercury? Is it one of the moons of Jupiter? Is it like one of the moons of Saturn?" And you're like, "No, it's our moon. We don't often see it from that side." Sometimes we would often call that side of the moon the dark side of the moon, and of course that's not true. The other side of the moon receives just as much as light as our side does. When our side is not illuminated, the other side is. So instead, we now call it the near side and far side of the moon. And let me bring it back up here.
I could definitely see how someone could look at the far side of the moon and think that it's Mercury. It does have that dippled look to it.
Yeah, no, it totally does. Okay, so this is a mountain range on the moon, and it's actually the highest mountain range on the entire moon. It's called Mont Montes Apenninus, which is also named after the Apennine Mountains in Italy, again, because they were named by the Italian astronomer. They probably formed about 3.9 billion years ago as well. The whole range, so it's extending from here to here, is about 600 kilometers long on the moon's surface, and the highest peaks reach about 5 kilometers. So not as high as mountain ranges are on Earth, but certainly still a very high mountain range on the surface of the moon. Actually, we'll get maybe a little bit of a brighter view of it here. and kind of closer to true colors. There you go. So a quick tour of the moon. Since it's out and it's bright, one of the things that we're a wee bit worried about today is that there is some haze in the upper atmosphere, and it may be being illuminated by the moon. So we do have some fainter objects on our list. They may not show up today because of the moon and its glow, but we'll see what happens. So there we go.
I think before we leave the moon, I think it's worth mentioning that if we do ever end up having commutes or more frequent touristic travel to the moon, I can definitely imagine lunar mountaineering being a thing. So how mountaineering on Earth and the desire to conquer the peaks of Earth has been a huge trend in our recent humanity. I can see that happening on the moon. That'd be something peculiar and incredible.
And probably, like, really dangerous, but I would be into it. I think that would be super cool. Yeah, imagine it, especially if you're, like, a mountain climber. That's one of your things. Isn't Joanna's a mountain climber, isn't she?
I think so.
Yeah, I think Dr. Wu is a mountain climber. In fact, if I minimize this, I think this is a picture of her climbing this mountain on the desktop of the computer. I have to confirm that, but I'm pretty sure. So there's a photo on the desktop of the planetary or the observatory's computer, and I'm pretty sure that's Dr. Wu on the side of that mountain. So, yeah, there you go. Have to ask her. We'll ask her if she ever wants to climb a mountain on the moon.
Oh my gosh, if that's her, I'm shocked and amazed.
Oh, question about the mountain range. Is that the edge of a large crater? No, it's actually another one of the seas. This is the Sea of Serenity that mountain range borders. So, yeah. And as Pride was pointing out, it might be easier to climb the mountains because of less gravity. But I'd also imagine that they are very, very sharp. Those rocks would be incredibly sharp, and so you probably have to worry about that.
And the gear you would wear, I mean, climbing up to Everest, you have to have a lot of gear to begin with and oxygen, but if you were climbing on the moon, you'd have to wear a lot more, which you might not be as heavy, but it'd be harder to maneuver and use your hands and fingers.
Yeah, no oxygen at all. Wow, yeah. Anyways, okay.
Yeah, it seems like we're having a bit of issue with sound again. I might be quiet.
I'm going to see if I can boost you up a little bit more. Let's see.
Thank you in the comments for pointing that out.
Okay, let's see. Okay, try your audio again, Sarah. Let's see if you're a bit louder.
Hello, this is Sarah. I hope you can hear me.
Hopefully that's coming through. Sarah's now been boosted by 5 decibels, so hopefully that's a little bit louder.
Excellent, thank you very much.
All right, moving on.
After this excellent tour of the moon, let's move on. We're going to leave our solar system completely. We're going to leave our galaxy completely. And we're going to head over to N63, the Sunflower Galaxy.
All right.
And when you're using the observatory, space travel is a lot easier. It's just a few clicks of buttons away.
All right. Try to see how you can do for the imaging. Okay, so I'm just getting the dark files loaded up. And the flats. Okay. And start stacking the picture. And see what happens. There we go. saw we also had a couple clouds rolling in here and there, so I don't know what's going to happen, but let's see.
We'll keep our fingers crossed.
Fingers crossed. So while we're imaging, Sarah, why don't you tell us a little bit about the Sunflower Galaxy?
Right, so something worth mentioning is that objects in space have a few names because different people find them and they name them different things. So you have the colloquial name or the common name, the Sunflower Galaxy, and you'll hear all sorts of different names. I've heard of things like the Hamburger Galaxy or the Sombrero Galaxy, and it's always a peculiar thing to hear these strange names, and sometimes you wonder, how did they see that object? The Sunflower Galaxy is just a mere 29 million light years away. And that's actually, I mean, it is pretty far away, but the nearest spiral galaxy neighbor that we have is 2.2 million light years away, and that's Andromeda. Sorry, just to pause here for a moment, I think in the chat we're still having a bit of issues with my voice not coming through.
Okay.
I wonder if it might be my own microphone. I'm going to give my microphone just a quick change.
Okay.
How does this sound? Hopefully this comes through a little bit better.
All right. How does Sarah sound now? I'm actually going to mute myself, so hopefully I'm not echoing that way.
Okay, I'm going to continue on, but if I continue to fall out or if my voice is not strong enough, please do put it in the chat, so thank you. Oh, perfect, we can hear Sarah now, that's great. Oh, not yours, Sarah. Okay, well, let's hopefully it'll resolve. So the Sunflower Galaxy, the reason why we are stacking this image, so for those of you who are not familiar with astrophotography, you can't just point a camera up to the sky and take a picture. Well, you can. You can attach it to a telescope and take a picture, but the objects are so far away that the number of photons that reach your camera chip are, in other words, diluted. They're quite weak. So you need to actually extend the exposure of your camera, of your picture, in order to get an image with more light. So that's the reason why we're doing a long exposure for the Sunflower Galaxy. Unlike the Moon, which is incredibly bright, galaxies, because they're so far away, tend to be quite dim. And people can ask us, how far away can you see with the telescope? And the question isn't so much how far away can you see with the telescope, it's how dim can you see. So, for example, the object that we're going to be looking at, the Sunflower Galaxy, which is also known as N63 in the object number 63 in the Messier catalog, it is 29 million light years away. That means the light that we'll be seeing has been traveling for 29 million years to get to our little telescope. Now, we can see this with a telescope because it's a rather bright object. There are billions of stars in this object, about 400 billion actually estimated. However, an object which is much nearer, such as Pluto, for example, which is a mere 6 light hours away, we can hardly see it with a telescope because it doesn't reflect much light. So galaxies produce their own light with the 400 billion stars that are within it, but Pluto doesn't produce its own light. It only reflects the light that it receives or that it reflects from the sun. So you can imagine that Pluto is rather small. If you took a cross section of Pluto, it would actually fit within Russia, which is quite, when you think about that for a second, that's quite a small object. So the light that travels from the sun has to hit Pluto and then come back to Earth. And so that's why we don't actually see Pluto, even though it's quite close by. So when people ask how far away can you see with a telescope, the question actually is how dim can you see? So we have a rather powerful telescope. The diameter of our telescope is 70 centimeters. It's one of the largest publicly accessible telescopes in British Columbia, which we're very proud of. And the Sunflower Galaxy, you can probably see it coming out now. That bright spot in the bottom right-hand corner of the image, that's the core of the galaxy, I believe. And Matt's just playing around with the stretching of the image to see if we can bring out a little bit more. But as Matt said, the weather today is a little bit on the dodgy side, so we might not be able to pull everything out. However, it is worth mentioning that this image, the Sunflower Galaxy, you may have actually seen it before. It's quite a popular image. And I think Matt is... Oh yeah, no, I'm just mesmerized right for a moment there.
Yeah, we're having there's definitely a lot of glow in the sky today, so it's having trouble like being able to stack and align the images with one another, unfortunately. If you want at some point, we can use our cheat picture, because I have it, if we want to.
I think that'd be wonderful. Yeah, let's take a look at that, because I think a lot of people would actually recognize the Sunflower Galaxy. It's a very popular object. Mm-hmm. It's quite beautiful to look at, and the formation of it, or the arms of it, are quite mesmerizing.
So that is what Sunflower looks like. This is through the Hubble Space Telescope, so of course it's going to look a lot better than ours. But you can tell it actually has that kind of sunflower look and shape to it.
I think we don't have... Oh, there we go. Perfect. The live stream was just taking a second. There you go. So you can see it's quite a beautiful galaxy, and it's tilted on the side. So galaxies, you can think of them as plates, right? They're rather thin compared to their width or their diameter. So this particular galaxy, it's kind of like a plate that's tilted facing you just a little bit. You can definitely see galaxies where you see them edge on. That's if you were looking at the plate on its side. And then there are galaxies which are face on, and we'll see that later tonight. And that's those are some of the most spectacular galaxies. But here you really get a sense of depth. So this galaxy is not your typical spiral galaxy. It's got kind of a mushy look to it. I believe, what's the term for it here? Let's take a look. Flocculent? I can't pronounce that word. But it doesn't have very distinct arms, but I think that makes it rather beautiful.
All right, cool. So there's a question about stacking in terms of how many frames are being put together. So it's one frame every 20 seconds is being added into the picture. Unfortunately, however, if the computer can't see the background stars clearly enough, it's not able to align all the frames together. So if you look down here, for example, there's an overview of the live stack and how many pictures are actually being put together on it. And so we have one photo that has been stacked, but 15 frames that have been ignored. So there's only 20 seconds of total exposure time on this one. And the main reason for this is that right now there is like some higher haze in the upper atmosphere, and the moon is glowing and hitting all of that haze. So we already knew that galaxies would probably be an ambitious target for the evening, but we thought we'd give it a shot anyway. All right.
Yeah, I think considering the sky condition, maybe we should try Whirlpool, considering we've got a cheat image for that.
And it's less cheaty because it's actually taken with our own telescope. Yeah, okay. So let me move over to that target.
So the target that we're going to talk about is called the Whirlpool Galaxy. It's another iconic object. It's actually one of my favorites. And the reason why it is because for the observatory, it was where we took our first light. So when we opened up the telescope, we first pointed it towards Whirlpool. Now, the Whirlpool Galaxy is a very peculiar one because it's actually a combination of galaxies, and you'll see it. There are two galaxies that are interacting with one another. It's called a Grand Interacting Spiral Galaxy. Quite a large term for a very large system. And this particular object stays rather high in the sky, which makes it great for astrophotography and viewing. So if you want to maximize the conditions of your nighttime observing, you want to point as far up as you can, up towards a direction called zenith, which is right above your head. You can imagine if you're pointing near the horizon, you're actually going through more atmosphere. The photons are traveling through more atmosphere to get to your telescope than if you were to point straight up. So Matthew has now moved us over to the Whirlpool Galaxy, and we're starting to take our images and stack them. It is quite difficult because the conditions are not in our favor, but you are in luck because we do have a photo that we actually took with this telescope. And it's actually one of my first image imaging projects, which was quite a challenge.
Do you want me to bring it up?
Yeah, let's bring it up.
Okay.
I think it's worth it. I'm too proud not to.
Yeah, it is a very cool picture. And so this is When did you take this one, Sarah?
Well, actually, you and I, we took this one in 2015, I believe, and Dr. Howard Trottier, who founded the observatory, he put a lot of guidance and a lot of help into processing this and giving feedback into this. So you can see here we have two galaxies. So there's one on the bottom, it's kind of the orangey blob right there, and then you have your more traditional or more typical spiral galaxy, the blue one up there. And I think it's just incredible because here you have two galaxies that are interacting with one another, and you can see that the smaller one on the bottom is actually being pulled in by the gravitational pull of the larger galaxy. And over billions of years, they'll actually merge into one, which I think is just incredible. Now, this object is 23 million light years away. The diameter of the larger one is about 60,000 light years. To give you a reference, our Milky Way is about 100,000 light years in diameter. I believe that's relatively a good estimate. Now, if you take a look, this is something really interesting. So take a look at the picture. There's the word galaxy at the bottom. Just above the second A of the word galaxy, if you look straight up towards the galaxy, it's about a third of the way up to the bottom galaxy. You'll see a slanted line. It's like a diagonal line that's pointing up towards to the right. That slanted line is actually another galaxy in the background. Right there, exactly, which is just incredible. So you remember we were talking about how galaxies are like plates? This is a galaxy that's actually on its side. So the galaxy in front of us is a plate, it's facing forward to us, and then that galaxy down there at the bottom is a galaxy, probably millions of light years in the background on its side, which is just incredible. And someone is pointing out in the chat here, hi Lee, by the way, nice to see you, or to see you active online. The spiral arms are a site for the birthing of new stars, which is quite cool. So anyway, I'm done being this is my favorite object. I don't know if you can tell, but I'm quite in love with the Whirlpool Galaxy.
It is a very cool picture. Yeah, brilliant. And again, like Sarah was saying, it was the first object that we imaged with at the first light of the telescope, right? And I think back then it was just we did one quick 1 minute exposure, just black and white, or like monochrome image, like didn't even have any color or anything like that at the time. Yeah, cool. All right.
Zena's pointing out galactic cannibalism. I call it that exactly. When one galaxy is consuming the other.
Consuming the other one, yeah. Which ours has probably done in the past as well. We've got another nebula. Now it is likely not going to show up, but it is the second last of the fainter objects we're going to try, and we have more cheat photos for that one. So after those, we're going to go more to point sources like globular clusters and lights of stars, and so we should be able to see them. So this is the Elephant Trunk Nebula we're going to try next, and let's see if we can actually find it.
What better way to spend a Friday night, honestly?
So we're moving to the other side of the sky on this one. And because this object is faint and it's even lower on the horizon, there's probably even less chance of being able to see it. But we will try and see what happens. It's unfortunate in one way. The moon is always great to look at, but it is unfortunate the last couple starry nights we've had that the clear nights always line up on days when the moon is so bright. It's always fighting against the moon.
And the moon is made out to be this romantic, object in the sky. It's this point of attraction and romance and reflection, and really astronomers are just completely peeved by the moon. But
it's jealous. It's a jealous celestial object. It just wants all of the attention.
We need it for our tides. We need it for life on Earth, right? If it could just always be a new moon, that would be great.
All right, let's see if our nebula will show up at all. Oh, no, it looks like we're staring straight into a light. So there are some new lights that have been set up around the observatory, and unfortunately sometimes they shine straight into the dome. And I think that might be what is happening in this particular exposure.
So for those of you who don't know, the observatory that we're streaming from, and you can actually see the cameras on the left-hand side of the screen, is the Trottier Observatory from SFU, and it was opened in 2015. It's an incredible observatory with the goal of educating the public. But we're always, I would say there's, a little bit of conflicting interests when it comes to the observatory and the rest of campus. We prefer darkness and we prefer no lights, and of course that's not exactly a key safety feature of a campus. So we're always in a little bit of a struggle and a little bit of a tussle to get dark nights and no light.
It's one of those things that it's kind of on the to-do list for things we'll be able to deal with more directly when everyone's actually back on campus. Because remember, none of us are there, right? So we are running everything remotely, which is why we have all these setups and often some technical issues. So one more sheet on this one then. This is the Elephant Trunk Nebula. Let's get it out of here. It's actually one of my favorites. It is very cool. So you can see how the nebula itself kind of looks like an actual elephant trunk. And the formation that you see toward the end that has that kind of like cavity in it is because there is a massive star called HD 206267 that is inside the center that is blowing out this kind of hollow cavity at the end of the nebula's trunk. It is an O-type star, so stars are classified by letter. O is the often the most massive of the hottest out of all of them, and it is has a binary star that orbits around it every 3.7 days. Now the cool thing about that is that with these stars together inside of this one section of the nebula, they're creating winds of radiation that are ripping through the cloud at 3,200 kilometers per second. Now the whole trunk is a region of star formation. So this is all the raw material that stars need in order to form. However, when you have one big star like that that's in a region, what it can do is actually blow away what we call is the protoplanetary disk. So this is the raw material that's orbiting around other stars that could eventually coalesce into other planets. And so if you have a star like this that's near you, it could steal your embryonic planets away and just blow them off into space. So you might have a bunch of stars that are completely stripped of their ability to create protoplanetary disks. This nebula is 2,400 light years from Earth. There are several young stars less than 100,000 years old that have formed in other parts of the trunk, and it's in the constellation of Cepheus. It also happens to be the first astrophoto I ever had on my wall. It's one of the reasons why I thought I'd put it up tonight. There's a little bit of nostalgia because it's actually above the horizon enough now at this time of the year that we can look at it if we weren't staring straight into a light bulb. So, there you go.
Beautiful.
Yeah.
Beautiful.
Elephant Trunk Nebula. All right.
Who says scientists are not creative? I mean, sometimes we have some pretty boring and ordinal names for protocols and such. But when astronomers just get all the creativity, they look at an object and say, "Yes, this is the elephant's trunk," or "This is the veil."
This is a veil. Although I will say that coming up with the name for the future merger of the Andromeda and Milky Way galaxy as Milkomeda, I mean, I think we have 4 billion years to come up with a better name for that.
I think we really hope we do better.
Yeah.
And that brings us to the name. It's not a particularly attractive name for our next object, the Dumbbell Nebula. I don't know why it was called this. Maybe all the other cool names had run out. And then actually there's another object called the Little Dumbbell Nebula. So I don't know why they used that name twice when the first time it still didn't quite hit home. But anyway.
Also pretty low on the horizon, this one, so we'll see how it turns out. If not, I think we have a photo of it somewhere that we can show as well.
Oh, we absolutely do have a photo. It's actually a photo we took straight Observatory. Zena on the call, myself, we were part of the team that took this picture, as well as Rohit. So that's quite. I think it's quite an exceptional object.
And I think this is also going to be too near some of the lights looking in this direction. Do you know where that photo of Dumbbell is?
I believe it's in the file that I sent you.
Oh, is it in? Okay.
I'm pretty sure it's there.
Perfect. Okay.
Otherwise, I can quickly zip you another copy, or send you another copy.
Oh, it totally is.
So The Dumbbell Nebula is really
There
close
you go.
to home. So the object that we were looking at, the last one that we spoke about, the Whirlpool Galaxy, that was 23 million light years away. So the object that we at is really close to home. It's only a mere 1,200 light years away. So you can see here, this is a planetary nebula, and it was discovered by Charles Messier in 1764. So it's a part of the Messier catalog. The object number in the Messier catalog completely escapes me right now. Oh, M27, it says right on the photo. I had quite a bit of foresight when I was writing that. So it's object number 27 in the Messier catalog, and it was found by Charles Messier. So this is also a very popular object to look at, and you can see the different colors. This is different types of gas being ionized. So nebulae are interesting. They are not stars. There's no rocks. It's gas. And if you think of it like this, think of it like this. So when you're passing down the street and you see those business signs that have those neon open and close signs, the way that works is it's a tube with gas inside. And when you turn on the switch, you pass an electrical current through this gas, and it excites the gas. In other words, it ionizes it. And it releases photons, particles of light, at a particular wavelength. And that wavelength translates into a specific color. So the type of gas dictates the color that you see when you turn on that electricity and you excite that gas. So that's pretty much what's happening here. There's a star nearby that's exciting this little bubble of gas, and that energy from the star is ionizing it, and the gas produces photons at a particular wavelength, and that wavelength is unique to the gas itself. So the red gas is a mix of hydrogen and helium, and the blue gas is a special type of oxygen called oxygen 3. So it's not the oxygen that we breathe. So don't go here thinking that you can just take a deep breath in and you'll be fine. Many things will happen to you at once, and either way you'll die a very painful and horrible death. But it's just beautiful to look at an object where it used to be a star. It was a star for quite a while. It expanded, collapsed, expanded once more, and then as it collapsed, it left behind this shell of gas of hydrogen, helium, and oxygen, which is quite, I think, special. And different color gases will indicate different colors of light in a nebula will indicate different gases. So, yeah, the difference between a galaxy, between stars and nebulae is planetary nebula, this kind of nebula, is sometimes left behind by certain kinds of stars, which is quite cool. We forget how different things can be in space. Oh, and my mom is online, so hi, Mom.
Hi, Sarah's mom. Yeah, so if someone in the future is looking at our own star, this is what they will see in roughly 4.5 billion years or so. So if someone's far away looking at our own sun, this is the same thing that it will deposit into the universe as a planetary nebula, which is kind of actually a holdover name. So in the past, before we knew what these nebulae were, we thought maybe they were other planets. And so they were called Planetary Nebula, and then that name just kind of stuck even after we knew that they weren't, planets anymore. It's another great and amazing photo by Sarah.
And team, don't forget, Xena and Rohit were definitely a part of it.
Nice. Yeah, good job, everybody. Actually, I'll tell a fun story. Can I tell a fun nostalgic story? Okay.
We love stories.
So back in the day, I happened to meet this incredible professor named Dr. Howard Trottier, that some of you might know. You were listening. He was on the stream last week, and he's also the founder of the Trottier Observatory. So this is when I was still trying to get involved with the astronomy community up at SFU, and I had sent him a couple of emails. And because he's a very busy man, he didn't have a chance to write me back. So I finally just crashed one of his classes. And I was like, hey, I'm really interested in astronomy, and I don't know if you're doing science outreach, I want to help. And he was like, well, what are you doing later on this week? It was like Thursday or Friday or something like that. I'm like, oh, nothing, I don't know. He's like, well, I'm going to set up my telescope on campus, and I'm going to image all night, and you can hang out with me if you want to. And I was like, cool. So we just set up on the grass with his telescope that he had brought out to campus, and we imaged the Dumbbell Nebula. That's actually what we took pictures of. And do you know where we did that, Sarah?
Is that where the observatory is now located?
It's where the observatory is now located.
Oh,
So we sat down
full
together.
circle.
We took pictures of the Dumbbell Nebula where at the time there was just like a walking path in grass. Like there was nothing actually there. And he brought with him, his pockets were full of black garbage bags, because he would walk around and cover up all the lights, some of them that we're having problems with, a simpler way, but walk around and cover up all of the lights around it so that we had better images of the dumbbell.
Dr. Trottier is such a character.
No, very
what a
handy,
wonderful,
handy
wonderful
man.
guy.
Okay, so moving on. What's our next one? I think we're off of faint objects now, so we should actually be able to see some of the stuff on our list.
You are right. We are now, so we started off with galaxies, we started off with the moon, my apologies, moved into galaxies, then we moved on to nebulae, and now we're into clusters, so star clusters.
So
I believe we're on M3.
M3 Globular Cluster. All right, let's give that a try.
I've mentioned this before, but I honestly can't think of anything better to do on a Friday night other than look at stars. I mean, I wish it was actually, on normal circumstances, we would open up the observatory physically to people, and we would have 300 people at an average come by the observatory to take a look through the telescope. And we used to have these massive gatherings of people that just look through the telescope, and hopefully that's something we'll do again in the near future.
Yeah, I miss everyone. I miss seeing all of you in person. Having these conversations in person, waiting in line, anxious to get inside and take a look at everything.
Looking at the sky and hoping a cloud doesn't cover your sight just as you're lining up to get a look in.
Exactly. All right.
Well, actually, when we do open up, here's a tip. If we do open up, come near the beginning or the end, because usually these sessions are 4 hours long, so come right at the beginning or right at the end, and that's when it's the quietest. In the middle, hour 2 is when it's the busiest.
Look, stuff! We can see something! Amazing.
Oh, yeah.
Now, the question is, can we get more than one frame to stack? Let's see. We did 2 frames! Yay! Okay, so we're actually doing some real imaging now. Woo! Take that, moon. Can't hog the entire sky. All it took was a cluster of thousands and thousands of stars, but we did it. We managed to see something through all of that moonlight. All right, here we go.
Biggie.
No biggie.
And if you're curious what the images on the left-hand side of the screen is, the top one is a view of the campus of the observatory facing east. The middle one is the actual inside of the dome. So you can see the telescope there pointing nearly up, and the dome is actually rotating right now. And then the bottom image is facing westward, so you're seeing the other side of the observatory. And you can see some of those little nefarious lights that we're quite grumpy about.
We are grumpy about them. We miss you too, Lee. We miss you too. Alright, I'm just gonna play around with this a little bit more.
You can see Matt's putting in a bit of effort to stretch the image. So there's quite a bit of work that goes into astrophotography. Some of those cheat images you saw that came up, they take dozens of hours to process because they're actually a compilation of hundreds of images. So for us to be able to show something live time is quite remarkable.
Yeah, that's a good point. So Sarah, let's take like your M51 that you did. So how long did you work on that one photo?
That one was, I put in about 12 or 14 hours of playing with that by myself before I gave up, threw my arms in the air, and Howard came in and appeased alleviated my suffering by helping with that image. That image probably took him about 12 hours to process, I believe. That one image is, I believe, about I think it's like 120 frames that were stacked up on each other. Yeah, it's like taking by stacking, you're able to magnify the dim bits, and you're able to not overexpose the bright bits. So if you just take a long exposure image, you max out the pixels on the bright spots, and you lose that data. You can't tone it down. But if you stack the images instead, you can prevent the stacking of the really bright stuff, and you can increase the intensity of the dim stuff. So you can actually create a non-linear transformation of the image, which is really cool.
And what was that? I don't know if you may have already mentioned this, but what was the total exposure time on M51?
Um, but I don't remember the number exactly. I will pull that up and I will get you the right number.
Probably in hours, right? So at least.
Yeah, it's probably I would say it's about 5 hours.
Yeah, 5 hours of total exposure. So.
Between 3 to 5 hours, yeah.
Yeah, so it gives you an idea. Like even here, while we're doing the live streams in the evening, we might get a few minutes of stack time into an object, and already it's starting to resolve. But to get those really amazing bright images, we're talking about hours and hours of exposure time. Anyway, so what are we looking at? We can see a star cluster. I love globular clusters. I think they're astonishing. I think it's amazing that you can look up in the sky from Earth at nighttime with your eyes, and you can see one star here, one star there, one star there. But to think that you can have a whole cluster of hundreds of thousands of stars all in one place in the sky is absolutely astonishing. So a little bit about this particular star cluster. So this is Messier 3. It's about 11.4 billion years old. So most globular clusters in the galaxy are really, really old, like on the order of billions and billions of years. Most of them are probably as old as the entire galaxy itself. This one is 34,000 light years from Earth, and most of them actually float around in a big halo around the outside of the galaxy. Now, there are some theories as to how giant clusters of stars like this can form, because when we see stars form in our galaxy now, like in contemporary time, when we're looking in places like the Elephant Trunk Nebula, or if you did some of our streams earlier in the wintertime, like in the Orion Nebula, we're talking on the order of a few hundred or a few thousand stars, but not hundreds of thousands of stars. So we think clusters of stars like this form only during particular times in the history of a galaxy, and that's when the galaxy is rich in gases that are being funneled toward the center of the galaxy, or, like in the case of M51 in Sarah's photo, when the galaxy is interacting with another galaxy. And those interactions between the two galaxies stir up a whole lot of dust, and you can form these massive star-forming clusters of hundreds of thousands or even millions of solar masses all at once. And then if they form together like that, often there's enough gravitational attraction that they never really fully come apart. They don't stir into the rest of the galaxy, and so they stay together. And globular clusters like this, some of them might actually even have supermassive black holes at the center, like galaxies do, or, in this case, what we call intermediate mass black holes. So they're not stellar mass, like, say, a few masses of the sun, or supermassive, like millions or billions, but maybe a few 100,000 times the mass of the sun. This one was discovered in 1764 by Charles Messier. It contains 500,000 stars. It's also home to a lot of variable stars, so the stars that change in brightness over time. This one has 274 that have been counted altogether. And this one is particularly isolated. So we said that they kind of float around the galaxy's halo, and this one is 30,000 light years above the flat plane of the disk of the Milky Way galaxy, which is pretty awesome. And again, it's 11.4 billion years old. Remember, the universe itself is only 13.8. So, it's almost as old as the entire universe, this cluster of stars, which is pretty cool. So there you go. I don't know if I can sharpen it up even a little bit more. There we go. Oh, yeah, look at that. Oh, no, I can go this way. There we go.
I think someone mentioned in the comments who's responsible for counting all the stars in the galaxy. Oh gosh.
Well, now
hire a cell biologist.
Yeah, thankfully now it's automated. That's good. Why not just call the star cluster a galaxy? And the point of that is probably because it's part of the larger galaxy itself. So it's still considered part of the Milky Way. And remember, galaxies have in the order of hundreds of billions of stars. So even though this cluster has hundreds of thousands, it's still not in the millions or billions like a galaxy has.
And also keep in mind, galaxies are enormous. Our galaxy is about 100,000 light years in diameter, and star clusters can be definitely tens of light years, sometimes hundreds of light years in diameter.
All right, shall we move on to the next star cluster?
I think that's a fabulous idea.
All right, let's do it.
We are moving on to M5, another globular cluster. So there are different types of star clusters, and Matt used a fantastic analogy a while back that I really enjoy, employing. So if you think of a star as a house, a star cluster is a community or a city. It's a collection of stars. And if you think of a star cluster as a community or a city, then you can think of a galaxy as a country. So just to give you an idea, a comparative idea in terms of size. Now, there are different types of star clusters. So you can have a globular cluster, and another big category are open clusters. And so what you saw was a globular cluster, and you could probably see that look towards the core, it gets quite dense. The stars are quite close to one another, and it's hard to discern the border from one star to the other. And that gives you an idea of the age of the cluster. Oh, so we actually have here something popping up on our stacking, which is great. And Matt is using flats, so flats help subtract the noise and the messy stuff from the background, so we get a cleaner picture. So star clusters, globular star clusters are older than open clusters, and it has to do a little bit with the size. That's a giveaway of the age. So as you can imagine, if stars start to drift towards one another to a central point of gravity, the more amount of time you allow for them to drift one another, the closer they'll get to one another. So as time passes, these stars start to drift together and they become more globular, more dense. And open clusters are, for example, like the Seven Sisters or the Pleiades. They are more distant and they haven't had time to drift closer to one another to that central point of gravity. So globular clusters are older. You can tell by their dense collection of stars. And another way to identify an old star cluster is by looking at the color of the stars. So the color of the stars is indicative of the temperature, and is a general rule of thumb that red stars tend to be older than blue stars. So blue stars burn bright, they're hot. Blue stars are hotter than red stars, and they're younger than red stars. So when you look at a star cluster, you see far more red stars than blue stars, an overwhelming amount of red stars. You can generally lean towards that this is a bit of an older star cluster. However, in this case, this star cluster, it's called M5, so object number 5 in the Messier catalog, is it's only a mere 25,000 light years away, by the way. And there's about 100,000 stars in this cluster here. And it's one of the oldest clusters in the galaxy that it belongs to, which is our galaxy, the Milky Way. It's about 12 billion years old. And if you remember, Matthew was saying that the universe is 13.8 billion years old. So to have something that's 12 billion years old is quite old. But there's something called blue stragglers in this image. You might be able to pick out that there are some blue stars in there. It's a little bit difficult, so don't beat yourself up if you can't see it. The sky is not favorable at this moment, but there are some blue stars in here. And Matt just told me a little while ago, I just learned this actually, is that some of those blue stars are called stragglers. So they're not actually true blue stars in the sense that they started out and they are still young blue stars, but they, by other means, became blue stars. One way is by merging. So two stars, when they get really close towards that dense core, as they drift towards the central point of gravity, they might actually smush up with another star and merge. And that actually might start the whole process again, starting new with a star burning very bright, very hot, and very blue. So while the two, it's actually a composite, or what is the word, like a result of two stars. It's actually not a genuine new young blue star. So that might fool you to thinking that an old globular cluster is actually young when it actually isn't. So please correct me if I'm wrong, though. This is just a new concept to me. I was baffled. You learn something new every night.
Cool. All right, yeah. So this is resolving pretty well. Again, another one of these crazy clusters. A cool factoid about globular clusters that you've probably heard me share before is that, you think about it like this. Between us and the closest star system to our own star, which is Proxima Centauri, is about 4.2 light years. In between here and there are no other stars, just a lot of like rocks and comets and void of space. And the Voyager space probe, which is heading out, not quite in that direction, but it is out there in space. In a star cluster like this one, like Sarah was saying, the star clusters are only tens or maybe even up to 100 light years across. So within like a similar area of space between us and Proxima Centauri, there might be 1,000 stars, or 2,000 stars. So that means the stars are so densely packed together that if you happen to be on a planet, we don't know if there are planets in star clusters. I don't think we found any exoplanets in one yet. But if there were planets orbiting a star in the cluster, there would be so many stars in the sky that there actually wouldn't be a nighttime. It would be so bright from all of these stars next to you that you'd have like a daylight constantly, no matter what direction you were facing.
I remember you telling me that years ago, and I still can't get over that piece of information. If you were on a planet, if there happened to be a planet around one of these stars, there just wouldn't be night. It would be so bright. Could you imagine that? That'd be horrible. Not horrible. I mean, that's not the right word. But if you're an astronomer, that's, the definition of unideal working circumstances.
Yeah, it's astonishing to think of what the sky would look like inside of one of these clusters. It would be incredible. All right, moving on. We've got one more cluster in our list.
We're actually doing really well. I'm impressed.
Yeah, it's actually stacking fairly okay. This is a pretty good indication of just how you can have clear skies, but they still are not necessarily good quality. And this is an example of that because these clusters are quite bright. And normally we don't have a problem stacking them at all, but even with this bright cluster, the computer has pitched 4 of the frames that it wasn't able to align. And so so the sky is still a bit hazy and muddy out there, unfortunately. But because it was clear, we said, hey, let's take the risk. All right, one more cluster, and that is Messier 13, also known as the Hercules Globular Cluster, so called because it is in the constellation of Hercules. All right, let's see what comes up. There it is. Hooray. The Hercules cluster, Sarah, was the first globular cluster I ever saw.
Oh, that must have been a special thing.
It was the globular cluster that taught me about globular clusters. The other thing that's really cool about these is they're actually quite easily visible through the eyepiece to your actual eyeball, not just to cameras. And so I really enjoy looking at these through the eyepiece and sharing them with other people through the eyepiece. It's one of those other things I'm really excited to do. I was talking to someone recently about telescopes, and I was sharing a factoid about just the nature of looking through a telescope that Howard had shared with me once, and he said, think of it like this. The light that comes from one of these objects, thousands of light years away, streams through space, and in the form of photons, right? Like you think of it like individual raindrops of light. Well, the ones that enter, say, our telescope are going to be unique from one object to the one that might land at a telescope a few kilometers away somewhere else on the Earth. That means that those few particles of light that came from that one object that you're looking at are unique. They've traveled through space for thousands of years. They landed in the telescope, and they ended their journey after all of that time in your eyeball. Isn't that something to think? They traveled through space just to meet you. And I think that's an astonishing way to think of your connection to space by looking out at the universe.
It's such a beautiful concept too, because when you think about it, a lot of astronomy and a lot of cosmology in space is just understanding how small we are and how I don't like using the word insignificant, because I think space is significant to us and we are a part of space, and space is a part of us. But it shows us just how small we are, and how when we do have that connection with space, it's quite special. That's
yes.
it's very much a science, but astronomy is this beautiful mixing ground between technical science and art in terms of interpreting and understanding and working with imagery, and then also, spirituality. No matter what sort of religion you walk from, the space is this place where you just look up and you think, oh my gosh. Every religion connects the sky to humans, so it's one of those sciences that it really encompasses the concept of science and Renaissance, just the whole person interacting with the natural world.
Yeah, absolutely. I am, so let's see here. So here is Hercules. Now I've turned up the gain on our camera a little bit, mainly because Hercules is a little bit lower on the horizon, and the computer is having problems picking out some stars to align to. They're there, but the computer doesn't see them necessarily as individual stars. So let's see if that helps a little bit. I want to get more of a stack on this one. But if not, this is one of the other ones that thankfully we have a cheat image for if we need to. And again, it's not super cheating because it actually is from our own telescope.
You can rest assured that Matt has gone the whole 9 yards to prepare for this, to make sure that every little detail has been thought of. So you are in the hands of a very well prepared person with a lot of foresight.
Hey, this was a team effort. Team effort.
Absolutely. Oh, absolutely. Just talking about space and selecting the targets and preparation for this is such a fun thing to do, because you think, oh, okay, what do you think people are going to like, and what do you think is up in the sky and good for us to see in the evening? It's always such an adventure to plan these evenings out for you all.
I'm going to change the binning on this picture and see if that works. So I'm adjusting something right now. It's called the bin. You might have seen it up here. I've changed my setting. This is a preset that's changed from bin 1 we had originally at 20-second exposures, and now we're doing bin 4 at 20-second exposures. Now what binning does is it changes the pixels on the camera and groups 4 pixels into one giant pixel. So you might remember on your own camera, on your phone, you might have something that is the number of megapixels on that camera. So what we're doing is we're taking clusters of 4 of those pixels and we're putting them together into one super pixel. It treats it as one big giant pixel. Now the advantage of that is what happens is you gather more of the light that are together in those pixels and amplifies in the light while you at the trade-off of resolution. So the picture's not going to be quite as crisp, but the light that comes from the stars is a little bit brighter, and what we can do then is hopefully make the stars more apparent to the computer so that it is able to align the frames better. And it looks like that's worked, because if you saw before, the computer was not able to stack any of the frames, and now instead we are stacking frames. So that actually might have worked a little bit better.
It always gets a little bit nerve-wracking when you're doing the live stacking, because there's so many little options and settings that could be tweaked.
And because there's 70 people watching you do it live at the same time.
Absolutely, absolutely. When you're working in the observatory, you can only fit 2 or 3 people into the control room, and then now you have 70 people watching.
Yeah, you have a whole audience watching you try to fiddle around with a picture. It is a little nerve-wracking, I'll tell you.
A little bit. But you're doing fantastic.
Well, thank you very much. I do appreciate it. I'm glad I have you for backup.
Oh, absolutely. Otherwise, I can just chatter our way through.
Okay, here we go. Yeah, so the stars, if you compare this, I don't know if you can notice on your side, but if you notice compared to the previous picture of the cluster we had, the stars look a little bit fuzzier. It's almost like they're a bit out of focus. And that's not what's happening. It's because we've grouped all these pixels together, so the resolution of the image has changed, but we're able to get more light from it now, so I can stack the pictures together, so we have this cluster. What I'm going to do, though, now, because you've seen a couple of these already through the telescope for the evening, I'm going to show you a completed photo that we have of the Hercules cluster that was done by Professor Howard Trottier. It's actually one of the first photos that was completed with the observatory. And again, this is an image that was taken over a number of hours in order to make the photo all together. And you can see just how much clearer and brighter all the stars are in this picture. It is a glorious, wonderful, incredible photo. So this is the only completed, like fully resolved and processed image of a globular cluster that we have done with our own library of curated pictures from the observatory, and it's one of my particular favorites because you just really get the sense of how many stars are in that cluster. A couple things to point out. So Sarah was mentioning earlier the blue stragglers. So you can see them in this cluster. You can see the very bright blue points of light. And again, these stars are a wee bit of a mystery, because if they are blue stars, well, those stars only last for a few million years. But the cluster is billions of years old. So why are those stars there? And again, as Sarah was explaining, it's likely that they are mergers between stars that have collided, because the cluster is so densely packed that you actually have stellar collisions happen. And it's actually important to note how rare stars will actually collide with each other. That doesn't happen very often. In fact, it is estimated, if they look at the computer simulation of the collision between the Andromeda Galaxy and the Milky Way, when it occurs in a few billion years, there's so much space on average between all the stars in those galaxies that both entire galaxies, one with 400 billion stars, Andromeda with 1 trillion stars, could merge and not two stars would actually hit each other. So the fact that you have these collisions of stars in a globular cluster is really kind of unique and interesting. That's why these kind of blue stragglers were a mystery for a while, and the one proposal is that they are collisions of stars. One other thing to note, and I know that I would be remiss if I didn't point this out, because Professor Trottier is quite proud of this one point in the photo. If you follow my mouse all the way up to this one corner, you will notice that there is a little fuzzy patch here on an angle, very similar to just above the title in Sarah's photo, where she pointed out there was another distant galaxy in the background. So there is actually a spiral galaxy way, way, way in the background of this one view of the globular cluster, which is pretty awesome. And I know Howard worked really well to process that one corner so you could get that galaxy out. So I want to make sure I'll point that out.
Something you can do to entertain yourself is look at astrophotography and try to find galaxies in the background or nebulae in the background. It's actually quite fun. Little game.
All right. Where are we going to next?
I believe, are going to the object I have very much difficulty pronouncing.
Oh, Accurate.
That
yeah.
one. There we go.
I think this one has been a common one lately. You might have even done it on the last Starry Nights, but I really like it because I think it's super cool. So let's find it. And we won't spend a lot of time on this one, but it's one of my favorite targets in the sky. And I found it because we were looking to, this is a binary star system, and we had selected in the past, we always use the one same binary star all the time. Oh, look at Xena. Yeah, M13 actually first attempt to image at the Trottier Observatory. I didn't know that. Look at that. There you go. So I'm going to switch back to more of like, rather than the stack mode, more to like the live stream mode. Here we go.
You can see the telescope in the middle stream on the left-hand side of the panel. It took a nice gentle sweep over. It's such a cool instrument. I'm just absolutely amazed by it. I think it's about 3 meters tall, like to the top of the arm, the white arm, not to the end of the telescope, but it's quite a big telescope.
We might be looking through a cloud.
A very rare event. They're hard to come by around here, clouds.
It does happen from time to time. All right, let's try a longer exposure, see if anything shows up. Where was I saying? Oh, yeah, so binary star system. So in the past, the one binary star system we always used to show was one called Albireo. And Albireo is, oh yeah, we're definitely looking at, I think we are in a cloud. Let's look at what our videos look like for the sky right now. The direction we pointed it. We might be a little bit too low for this one. Yeah. Boo. Okay. Maybe we can skip it. So the reason, what I'll say, because I was going to go on a mini rant, is that usually for the one binary star system we always showed used to be called Albireo. I guess we can go there instead. But one of the things about Albireo that we've since discovered is that it's actually not a true binary star system. It is a visual binary, but it is not an actual binary pair. So the two stars are not entangled in one another's gravity. So they appear to be a binary star, but they're not actually orbiting one another. This was for a matter of debate for a while, but it has since been resolved that, yes, Albireo is not an actual binary. It is a visual binary. So I wanted to find another binary star system that would replace it, and so we did Accurate because they actually orbit one another, but it looks like it's too low in the sky to be able to see. Let's see if Albireo will show up for us instead. Yes, too long an exposure. Okay, let's go back. There we go. So this is the visual binary known as Albireo, and it's often a common favorite among RASC members and targets with us at the Trottier Observatory, primarily because you have two stars that are very distinct in color from one another. So one that almost has a bluish color and one that has a reddish color. But even here, I think we're struggling to see it because there might be some haze still in the sky because my exposure is seconds long and they should be almost like bright points of light. So there might be some haze still low on the horizon. So maybe we'll move on to our last couple targets here instead because I think they'll be a little bit brighter than these ones will be. So what's next? I think Sarah wanted to talk about Navi.
Yes, I think you're right.
In the constellation of Cassiopeia. Again, also might be a little bit too low, but let's see what happens.
I believe Cassiopeia's it's circular, so it should be relatively higher up in the sky.
All right, let's see what happens.
Oh, I see what you mean. So Cassiopeia is one of those constellations which are circumpolar, and circumpolar means that it, from our perspective here in Vancouver, in the northern hemisphere, it stays above the horizon throughout the entire year. So the sky doesn't stay the same, of course, and throughout the seasons, different constellations dip below the horizon. So some stars and constellations are known as winter ones, such as Orion the Hunter, that's a winter constellation, and other constellations are more of a summertime constellation. So we're going to be looking at a star called Navi in the constellation Cassiopeia, and I believe Cassiopeia, in terms of constellations, is the woman sitting with a mirror, I believe. I really like Cassiopeia because it looks like a lazy W. It's not a super nice W. It's kind of like an awkward W. I just find it quite interesting. So the Navi is actually Gamma Cassiopeia. So when it comes to constellations, there are different names or different designations for the stars in the constellation. So the brightest one is called Alpha, and then the second brightest is Beta, and third brightest is Gamma. So we're looking at the third brightest star in Cassiopeia. So I think you can see it right there. It's a tiny dot, but that is what a star is. It's a point of light.
It's definitely going in and out. So I think we're looking at it through some moving cloud. So because it's kind of getting brighter and fainter and brighter and fainter. But yeah, it is there.
And the reason why this is particularly interesting is, I actually learned this just recently too through Matt. This star was used as a reference point for one of the Apollo missions. So the Apollo astronaut Virgil Gus Grisham, it was named after him, specifically after his middle name, Ivan. So Navi spelled backwards is Ivan. It was used as a reference point during space missions, and unfortunately, Grisham was one of the astronauts who died on the platform of Apollo 1 during the fire. So he was memorialized, I guess you could say, by this star. So as a point of navigation during the later Apollo missions, his name was put on this star. So It's about it's a star that's near the end of its life. It's ending. It's one of the normal stars. Normal as in like one of the stars that are on the main sequence, and it's about 15 times the mass of the sun. So it's quite big. So it looks like a small point of light in our screen, but we forget that these are quite big. Um, it's about 600 light years away, which gives you a moment there to appreciate just how far this light's traveling for us.
Cool.
And the next star we have, it's sometimes a little bit difficult to chat about stars because, as you can see here, they're a one point of light, like a point source of light. So it can be a little bit tricky to capture on camera. But also, some people look at this and they think, "Oh, that's it," and sometimes I can't help but respond with, "What do you mean that's it? That's a star that's burning." And the photons have just traveled hundreds of light years to get to your eye. What do you mean that's it? But I digress. So we're going to be looking at a very popular. Oh, check that out! I think we just had a satellite pass through our.
That was I think the telescope
no.
was still slewing. But a neat thing about
yeah.
this, Sarah, is you can see both stars in this picture.
Mm. Oh yes. So we're actually looking at Polaris right now, and so a lot of people know that Polaris is the North Star. It looks like it points north. I don't think I needed to explain that, but I did regardless. It's about 25 light years away, which is actually a lot closer than our last Navi, which was 610 light years away. And Polaris is actually a triple star system, and you can see two of them here. You have the bright one, which is Polaris AA, and it actually has within that. Oh, actually, no. Matt, do remind me. Do we see AA and AB here, or are we seeing all three?
This is so Polaris A and AB are within the one bright point, and then the second bright point is Polaris B. So what I'll do is I'll bring up an image here, and it kind of shows the diagram.
The orbits of these three stars are interesting, and it's easier to display it with a diagram rather than me fumbling through a verbal explanation, because it's quite a dance, actually.
Yeah, so the original one, so Polaris A and Polaris AB orbit each other, so they're actually together up here, and then Polaris B is way over here. So this is a more zoomed in field of view, this picture, than what we're seeing. So when we're looking at Polaris here, Polaris A and AB, so that's the primary star and its orbiting star, are all in this one glowing ball, and then this is Polaris B, its companion that's orbiting, or they're all orbiting together. There you go.
Exactly.
I didn't think we'd see that actually, so that's pretty cool.
Yeah, I'm quite amazed. You can actually see the two main groups of stars there, and you can actually see Polaris during the daytime. It's not as fantastic. It's a little sparkling diamond. It looks like a sparkling diamond in the light blue sky, but it's quite beautiful. And so we know that this is the North Star, but because the Earth is, so as many people know, the Earth is tilted. It has a precession, so it's not rotating perfectly. It doesn't stay on the same angle all the time. The angle changes a little bit. So that means our idea, or where we see north, it changes. Or not, sorry, one moment please. Our view of the sky changes over the long run. So over thousands and thousands of years, the positions of the stars change. So the North Star won't always be in the north. It was Vega, which was a different star that we'll go on to later on, was a North Star about 12,000 years ago, and then we slowly drifted towards Polaris being our North Star. So for your lifetime and my lifetime, the North Star is the North Star, but I think we'll have to revisit this in about 10,000 years and recheck this fact.
Yeah, and we were around then. You know, that's the thing that I find really fascinating, is that we think of the sky with so much permanence, but humanity has already been around long enough to see the sky change significantly, just in the 250,000 years that we've been walking around. So even in, like, during the Ice Age, the last Ice Age, then Polaris was not the North Star. You know, that's crazy. Like, think about that. That's incredible. You know, to think that, and that's from basically our Earth just wobbles around, just like a top. So if anyone's ever spun a top before, you know that a top wobbles. Where our planet does the same thing. Yeah, so it's called precession. And so the polar north of our planet wobbles around and eventually will point at different stars. And so in between, I guess we just won't have a North Star.
Oh, yeah. That actually brings us really close to the next object.
Yeah. All right.
We are still holding on strong. We have 65 people watching. That's incredible. We
Nice.
started off with like 75.
Thanks for staying late with us, everybody.
Yeah. I was telling Matt, I was a little bit nervous before this was happening because this is my first live stream. And I've done in-person Starry nights with no problem with hundreds of people. But the moment you put me in front of a computer with 60 people watching and I can't see their faces, I get a little nervous.
So Kurt asked how close to North Polaris is. It's pretty close. But if anyone who has ever aligned a telescope before will tell you, one of the processes to get a telescope to point properly is something called a polar alignment, where you will look through an eyepiece that has an etched-out carving of Cassiopeia, Big Dipper, Little Dipper, and where the North Star is. And when you look through that there's a telescope, like a mini telescope in the mount of other, like that where you put your telescope to do that alignment. And when you look closely, Polaris actually orbits around the North Pole slightly. So it's not right on, but it's really close. And as Lee was pointing out, only even 2,000 years ago, we didn't have a North Star. And even at the time that I owned my telescope, only 10 years I had my telescope, there were updates to the tracking software for precision based on the movement of the Earth. Yeah, just even in like a decade. Yeah, just to make sure it was so precise, even because our planet had already wobbled enough in 10 years to have to update my telescope's tracking software, that's astonishing to think about. Okay.
It's astonishing. It also makes you feel a little bit old. I mean,
yeah. I'm old enough to have witnessed the planet move on its axis. Yeah, that's pretty old, I guess.
I usually age myself by hearing the new slang that comes out, and I think, really?
Well, that's when I used to work at SFU with young students. Then, yeah, they usually kept me up at all the cool lingo. Whoa, what's happening? Okay, hang on.
This is beautiful. So actually, fun facts, as Matt is tinkering, I'll just jump in here and mention, so those lines, those spikes that you see, that's not actually an artifact of the star. Stars don't radiate light in spike formations like that. That's actually a part of the telescope. It's something called the crosshairs, I believe that is. It's if you've ever seen a telescope, a mirrored telescope, you actually have to mount the second mirror. And the things, so you have to mount the second mirror, probably tens of centimeters or about half a meter or a meter away from the secondary mirror, because you need to bounce the light in a way that it ends up in your eye. If you just use a mirror, you're going to reflect the light back into, and then, well, now you've lost your light. You're not going to be able to see it. So you need to have a second mirror which captures that reflected light and brings it back into the telescope towards your eyepiece, the periscope. And you can't just, you have to make sure that second mirror stays in place, and you use a mount. There are 4 bars that hold it in the center, right in the middle of the primary mirror. Exactly, refraction bars. Thank you, Lee. And those refraction bars cause the light to look like those spikes. That's actually an artifact from the refraction bars. So if you were to look at the same object with a refractor telescope, so a telescope which only uses lenses, you won't see that. But when you use a reflector telescope that uses mirrors, you will see that. And a lot of people think it's actually a really beautiful thing, and they actually try to enhance it. And I agree. I think it looks quite spectacular. But anyway, Matt, back to you.
Oh, no, that reminds me, because there's one more of Sarah's photos that we haven't seen yet tonight, and that's of the Bubble Nebula. And there are some stars that have specifically very pretty diffraction spikes in it. So since you brought that up, I remember that there was this one here that has a beautiful spike in it. Oh, there's the actual bubble. And there it is. That nice spike there in the picture.
Oh, yeah. Yep, there it is.
That's a beautiful photo. Another amazing photo by Sarah. Okay, so this is our second last object for tonight. This is the star Vega. So the reason why we brought this one up after Polaris is because as we were saying, Vega and the Polaris switch as the North Star based on the precession of the Earth. So Vega was the North Star 12,000 years ago. It is 25 light years away, and it was the first star to have its spectrum photographed, which is cool. So by spectrum, what we mean is actually, so if you remember back to when Sarah was talking about the illumination of excited gases from the Dumbbell Nebula, when certain gases are excited by energy, they glow at certain colors. And if you combine all those colors together, like in a star, you have to split them apart when you use like prism, for example. So if you take sunlight and you put it through a prism, you've probably seen it, it all splits out into different colors. So we can do that with stars, and we are imaging their spectrum, and that tells us what the stars are made of. We've also even started to do that with the atmospheres of distant alien worlds, which is pretty astonishing. We've been able to measure the atmospheres by measuring their spectrums or photographing the spectrums of distant planets to know what the gases of their atmospheres are made of, to see whether or not they might be habitable. This will become the brightest star in the sky. So Vega is not the brightest star. Currently the brightest star in the sky is still Sirius, which is the hunting dog of Orion, the hunter. But this star will become the brightest in 210,000 years. So because of the movement of the stars and our course of travel through the galaxy, eventually we'll become close enough to Vega that it will become the brightest star in the sky. And it will be so for about 270,000 years more after that. That's pretty astonishing. Now, Vega is really weird because it rotates very, 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 very quickly. It rotates at 274 kilometers per second. So to put that in perspective, our sun only rotates at 2 kilometers per second. Vega is spinning so quickly that it's reached 93% of its breakup speed. So it's almost spinning fast enough that it would just fly apart if it was spinning any more quickly. Now, why is this happening? We're not exactly sure. We think usually when stars have a rapid rotation like this, it's because of the interaction with another star that has maybe accelerated it. Another cool thing about Vega is that it was the first star to have a dust disk observed around it. We thought maybe that was a protoplanetary disk that planets forming around the star. It turns out now it might be just debris, kind of like an asteroid field that's orbiting around the star. But the detection of that protoplanetary disk sparked the imagination, considered maybe there was alien worlds around Vega, and that is why Vega was chosen in the book Contact to be the star that we were contacted by an alien civilization. And if you read the book Contact or seen the movie Contact, which is a brilliant movie, you should watch that film. Oh, actually, in that movie, kind of tying back to one of our previous targets, that movie, Jodie Foster spends a lot of time at the Arecibo radio array, which recently collapsed, unfortunately. But Arecibo was also used to beam a message. It's one of the few times we have messaged signals to space. We're often listening to signals from space, but it was one of the few times we messaged to space, and when we did that, we sent that message to the M13 Globular Cluster that we were looking at earlier. So back in the 1970s, we beamed a message into space that contained information about human DNA and a bit about our civilization to the M13 Globular Cluster. Although, I don't know if anyone's probably living in the Globular Cluster, but an interesting bet, I guess, to send it to that many stars all at one time. So there you go.
It's also quite far away. It'll take quite a while for it to get there.
Yeah. And as Sarah was pointing out to me when we were doing research on targets, that Vega is used as the calibration star for brightness. So we use a magnitude scale of stars in the sky, and Vega is magnitude 0.0. So every star's brightness in the sky is measured against Vega. It is used as the calibration star. How are we doing for time? Okay, one more quick thing. Since it's up in the sky and we haven't looked at any planets yet, we thought we would jump over to Mars.
We've actually got the timing really well down. I mean, we're a couple of minutes over, but we've only got one more object, which is Mars.
Yeah.
You figure we would bookend this entire session, a beautiful image of a bright, bright moon at the very beginning, and then we have Mars at the end. And so for those of you who are avid planet watchers, I'll be completely transparent. I thoroughly enjoy seeing Saturn and Jupiter. They are by far two of my favorite objects to look at because they're just so rewarding to look at.
Oh no!
And they're actually... Oh?
We might have waited too long. Well, it looks like Mars is beneath our visible horizon. But that's okay. Keep going. I have an idea.
No, not a problem, not a problem. I just wanted to let everybody know that if you are interested in seeing both Jupiter and Saturn in the same evening, Look towards mid to end of August. They'll be up earlier in the evening. You could probably see Jupiter and Saturn earlier in the season, but it'll be much later in the night. But if you're looking for Jupiter and Saturn in the evening at a rather earlier time, look towards end of August. It's quite magnificent. You can see both of them.
So we wanted to show Mars, but we went a little bit over time when Mars was visible on the horizon, so it's a little bit too low. But one of the reasons I wanted to chat about Mars is that, as you know, we have an active mission on Mars right now looking for signs of past life, and that is the Perseverance rover. But Perseverance is partnered with the first ever flying rover we have sent to another planet, and that is the flying Mars helicopter known as Ingenuity. And Ingenuity has done a couple test flights now, and it's shown that it works, which is awesome because it's challenging to fly in the Martian atmosphere because it's very, very thin. But at the very least, I want to show you this video if you haven't seen it yet. And this is the first footage of Ingenuity's test flight on Mars. So here you go. You can see it spinning up its rotor blades. Taking off. It's almost cute.
It's the first flight on a different planet.
First flight yeah. There it is hovering.
Incredible.
And I think it flies off to the right of the frame. Oh, maybe it just lands and touchdowns again. And then there was a lot of very happy and crying engineers. If people didn't know that, there's actually a swatch of fabric from the Wright brothers plane that went to Mars with Perseverance, and it's on the Ingenuity helicopter. So the Wright brothers plane represents the first powered human flight on Earth. So given this was the first powered flight of any of our technology on another world, they brought that with them and attached it there too. So you just witnessed the first flight of any of our technology on another planet, which is pretty astonishing. Yeah.
It's incredible to see how full circle it is.
Yeah.
That deep sense of symbolism again. And I've said it before and I'll say it again. I think science is far more spiritual than we give it credit for.
Oh yeah, for sure. And Carl Sagan would agree.
Absolutely.
That there's certainly a spiritual element to our trek through the universe. So yeah. So it's there's some really cool things going on right now in space. It is very likely that we may have maybe not a definitive, but a much more solid answer as to whether or not there's life somewhere else in the universe based on the couple of rovers that are right now on Mars. And think about that. Sarah, human beings have been on the Earth for 250,000 years, and we might be living in the one time in our history where we get an answer to that question, or at least a lot more evidence one way or the other. We might see people walking back on the moon again in even just the next couple of years, and we might see the first human walking on another world in maybe the next decade or two. So it's an interesting time for space exploration.
Oh, absolutely. I can't help but think and hope that the next few milestones that we reach will further unite us as humanity, as one big group of people on one rock spinning around this thing we call the sun.
Yeah,
Sometimes
absolutely.
I think we forget that.
Yeah. Great. So we'll wrap up for the night. A reminder to everyone that we have a telescope loyalty program. So if you are participating with our Starry Nights online, what you need to do is email SFU Science Outreach. It's just scienceoutreach@sfu.ca is the email address. And let us know what targets we saw tonight within 24 hours, and you can receive credit toward the program. I think if you participate in 5 events,
it's 5, yeah.
5 events, you get a telescope, which is pretty amazing. And so
which is so cool.
It's so cool.
Just think about that.
Yeah, so definitely participate. That is why there is a delay of 24 hours before the streams go online. So that's why they're not posted until later, if you're warning. So
I'll put the email down below, so in the chat box.
Yeah,
so this is the email that you contact.
Great.
SFU Science Outreach at sfu.ca.
Perfect. Yeah. So make sure you send an email there, and you can participate and sign up with our Telescope loyalty program. We will always let people know when the next show is going to be on the Trottier Observatory Facebook page and also on the email list. So if you want to be on the email list, again, also email us if you Science Outreach. If you are here, then you probably already are. But if there's anyone else you know that would enjoy this as well, then let them know. And share the wonders of space. Thank you, everyone, so much again. And those of you who also helped out in moderating tonight. So I saw Kyle and Zena and Lee. So thank you all very much for being in the chat. Sarah, thanks for joining me tonight.
Thank you so much, Matt. This has been an incredible exploration of our little place we call the universe.
Yeah, and so let's hope for more clear skies in the near future. Thanks again for joining us, for staying up so late. And remember to keep looking up.